Hey everybody, welcome back to chemistry. And we are now moving into a new chapter, chapter 6, which is entitled Energy Changes, Reaction Rates, and Equilibrium. So we're going to cover these topics, but the first thing we want to do is understand a little bit about what energy is, and then we'll talk about energy changes in chemical reactions. And so you need to have an understanding of what energy is. And so I think when most people think about energy, they think that, for example, a hot object has a lot of energy and a cold object has very little energy. And that is actually a true statement. But before 1800, we had a misconception as to what was causing the hot object to have a lot of energy. Before 1800, people actually thought that the reason why the hot object had a lot of energy is because there were a lot of atoms called energy atoms, or you can call them caloric atoms. I think that's what they called it back then. And that a hot object is hot because it has more of these energy or caloric atoms, while a cold object has fewer of these energy or caloric atoms. And so that was thought up to about 1800, but it was kind of figured out that if you took the mass of a hot object and cooled it down, the mass didn't change. So that suggests that energy has no mass to it. So energy really, we now know, is not any kind of matter per se. Rather, what energy is something that matter possesses. And so one of the most important things you can understand about energy is that atoms or molecules will possess energy by virtue of their composition or motion. So that I have on this slide here, and so we will move on to the next slide. So the first thing I want to do is talk about the basic textbook definition of what energy is. And so you'll see in the textbook that energy is often defined as the capacity to do work. So let me give you sort of a simple example of that. So let's say it's a hot day outside, and let's say you are asked to mow the lawn. And so you probably know that for you to mow the lawn, it's going to take some work on your part. And so let's break down why that's the case. And so you go out to the lawnmower, and what you'll have to do is you're going to have to push the lawnmower with some force over a certain distance. And so if you take the amount of force that you push the lawnmower with times the distance over which you push it, that will actually give you the total amount of work that you need to mow the lawn. Now, you probably know that you need energy to have that work done. So if you're exhausted, you're probably not going to be able to push that lawnmower. And so what you might do, for example, is before you mow the lawn, is you might eat a lot of food. And the reason why you want to eat a lot of food is to give you the energy for you to do that work. So energy allows you to do work. So energy has the capacity to do work. And so let's take a look at this example here of water behind a dam. And so I think you can imagine there that water behind the dam has a lot of capacity to do work. And so unfortunately, if the dam breaks, then you'll see the water doing work. And what will happen is the water will apply a force on a house over a certain distance, and it'll cause the house to collapse. So clearly, water behind the dam has capacity to do work. Now, in physics class, we'll take a look at the energy of that water behind the dam, for example, and maybe we'll break it down into two ways. We'll say that that water behind the dam has kinetic energy and also has potential energy. So let me talk a little bit about that. So the kinetic energy of the water behind the dam is where water molecules are moving. The water molecules have a little bit of mass, and they have a little bit of speed, a little bit of velocity. They're moving around, and so that gives the water some kinetic energy. But then there's other energy that that water behind the dam possesses. It's something called potential energy. This is the energy the water has due to its position at a certain elevation above the ground. And so what I want to do now is talk a little bit more about the differences between kinetic energy and potential energy. So again, kinetic energy is the energy that matter has because of its motion. So two things are required for an object to have kinetic energy. One thing is that the object must have some kind of mass. The other thing is that that object must be moving. So if that object has mass, but it's not moving at all, then it has no kinetic energy. And there's actually a formula there that you can use to calculate kinetic energy. And you see that it's the 1/2 times the mass of the object times the speed or the velocity of the object squared. But there's another form that is potential energy. Potential energy, your book defines as stored energy, but again, you can think of it as energy due to an object's position. So let me give you an example of that really quick. So let's say I have this pen here. And so let's figure out right now if this pen, which I'm trying to hold still, has any kinetic energy. Well, you know that kinetic energy is equal to 1/2 times the mass of the pen times the velocity squared of the pen. Now, the pen is not moving, so velocity is 0. So right now, this pen has no kinetic energy. But the question is this: does it have any other kind of energy? And I think you probably know the answer is yes. It does have some other kind of energy. So let's describe what this energy is. You know that when I let go of this pen, it will start moving. And so when it starts moving, it has kinetic energy because it has a certain speed. So we know that that energy going into the kinetic energy of the pen must have come from somewhere. So where did it come from? It came from the pen's potential energy. The reason why this pen has potential energy is because it's a certain distance away from a gravity force. When it's a certain distance away, it gives it a certain value of potential energy, which can all be exchanged into the kinetic energy as the pen falls. Now the question is, can we change the potential energy of the pen? And the answer is yes. If we have the pen higher, then now, due to its position, it's a little bit further from the source of gravity, and believe it or not, it has more potential energy. And the way we know that is if I release the pen, it's going to have a lot more kinetic energy as it falls down. So that gives you some idea of the difference between potential energy and kinetic energy. Now, what I want to do now is I want to do some simple problem solving, understanding when objects have kinetic energy and potential energy. So if I can blow up the slide. So let's look at the left side. And what we have here is a person swinging a pendulum. And so the way the pendulum was made was they had a washer and it's attached to the string. And this person is just swinging this pendulum back and forth. So it's here. And so now if you can imagine this pendulum moving, what you can imagine is this. When this washer at the end of the pendulum is as high as it can go, as you kind of know, then this washer is motionless. And so if it's motionless, then velocity is 0, and so kinetic energy would be 0. So here in this position, kinetic energy is going to be 0. Now, let's look at the washer when it's in the middle position. So in the middle position, you can imagine that this washer is going as fast as it can go. So here in the middle position here, as it is in the bottom of its cycle here, the kinetic energy is relatively high. Now here, when it gets back to the other side, the kinetic energy is 0 again because it's motionless. So what you can see is in this pendulum cycle, we have the kinetic energy varying from nothing when it's not moving. When it's in the middle of its cycle, it's going as fast as it can, so the kinetic energy there at that point is high. And then up here on the other side, when it's not moving, again, the kinetic energy is 0. Okay, so now we can also evaluate this washer of the pendulum in terms of its potential energy. Here, let's look at the washer again on the left, which is at its highest position. Here is furthest away from the ground. It's furthest away from the gravity source. So it's going to have relatively high potential energy. But in the middle of its cycle, when it has the highest kinetic energy possible, it's going to have a relatively low potential energy because here in this position the washer is closer to the ground, and then when it goes up to the other end of its cycle, when the kinetic energy is 0, the washer is as high as it can go, and so its potential energy is going to be relatively high. Now, one thing you may have noticed is that as the kinetic energy is going from 0 to high, as it's going to the midpoint of its cycle, the potential energy is going from high to low. And so essentially what you can see is you're having one form of energy, the potential energy, being converted to another form of energy, which is the kinetic energy. And so this is what you see quite a bit in matter. You have different forms of energy being converted from one form to another. Okay, so let's look at this roller coaster track and figure out where the car will have the highest amount of kinetic energy and the lowest amount of kinetic energy. Well, if you know anything about roller coasters, it looks like when it gets to the top here, right before you're about to go down, here you're going to have relatively low kinetic energy for the car on the roller coaster, right? And the reason why I say that is because I know the car will be moving a little bit, so it's going to have some kinetic energy, but as you get down to the bottom of this track, it'll be moving faster and faster and faster, and maybe at this point here, it might have the highest kinetic energy. And the reason is it's so high there is, again, because the car is moving very fast, and k is equal to 1/2 mv squared, so v is a very high number, so k should be a very high number. Okay, so let's evaluate potential energy. Well, the car here, when it's highest from the ground, is going to have the highest potential energy, and when it's closest to the ground, it's going to have the lowest potential energy. And again, you sort of see an example here in a piece of matter where you have potential energy of that matter being converted to kinetic energy. Okay, so let's move on. So this is kinetic and potential energy as maybe taught in physical classes, but we're in a chemistry class. So let's talk about how kinetic and potential energy are applied in a chemistry class. Now, in chemistry, you're dealing with atoms and molecules. So the question is, can atoms and molecules have kinetic energy? And the answer is yes. And the reason is, atoms and molecules have mass, albeit it's a very small one, and they're also moving around. So each little atom or molecule has some amount of kinetic energy. You can actually calculate the value of the kinetic energy it has is equal to 1/2 mv squared. Okay, so a simple example of that. So imagine you have a solid, and let's say you're looking at the solid at a cold temperature and again at a hot temperature. So the question is, does this solid in the cold or the hot temperature, does it have kinetic energy? And the answer is yes. It's because both in the cold and hot solid, the atoms or molecules in the solid are moving. So they're not moving around each other, but the atoms or molecules are in a fixed position, but they're vibrating back and forth. And they're vibrating back and forth. That means they're going to have a little bit of movement and they're going to have a little bit of kinetic energy. Now, if you heat the cold solid to the hot solid, what will happen is that the atoms or molecules will start vibrating even faster. And so they will have more kinetic energy. And it's for that reason that they have a higher temperature. So we can sort of see that solids definitely have kinetic energy. And so this would also apply to liquids and gases as well. And so liquids are similar to solids in that the molecules or the atoms are very close together. It's just that they're moving around each other. And they're probably going to have more kinetic energy than found in a solid usually. Now, with gases, they have tremendous amounts of kinetic energy. And the reason is in gases, the individual atoms or molecules are moving very, very fast. And so that gives them a lot of kinetic energy. So what you can see is most certainly chemicals can have kinetic energy because they're moving around. Okay, so importantly, chemicals, say molecules and atoms, have potential energy due to their particular composition. This is a very important point. So here the point I'm trying to make here is that importantly, different molecules have different levels of energy. So let me explain a great example of that. Let's say that you have glucose. Glucose is a molecule which has 6 carbon atoms attached to 12 hydrogen atoms and 6 oxygen atoms. And so all food has glucose in it. And we can utilize glucose as a source of energy. And the reason is because glucose, the molecules themselves, are loaded with energy. And there's something about the combination of carbon, hydrogen, oxygen, and the way the atoms are bonded together that gives this molecule tons of energy. And oxygen, which will react with the glucose in your cells, has a lot of energy as well. Now, what's interesting is your cells will take the glucose, will react with the oxygen, and they'll produce 2 new molecules that they are carbon dioxide and water. But the thing is, carbon dioxide and water have less energy than glucose and oxygen. So you can sort of see this diagrammed here. And so here on the y-axis, we have increasing amounts of energy. And then on the x-axis, we have the different kinds of molecules. And you can sort of see here
On the left side, the reactants here, we have glucose and oxygen, which will get into the cell. And so they have relatively high amounts of energy. But carbon dioxide and water, due to their unique structures and the way the atoms are bound together, they have relatively low amounts of energy. And so the point here to see is that molecules have different levels of energy. Glucose, because of its structure, just happens to have a lot more energy than carbon dioxide and water. So remarkably, we can use this to great effect in our cells. So our cells generate energy, and they pretty much do that through this reaction. They take advantage of the fact that glucose and oxygen entering your cells have relatively high amounts of energy, but carbon dioxide and water, the waste products from glucose and oxygen, have relatively low amounts of energy, and so the excess energy that cannot be contained in carbon dioxide and water is released into the cell. So the cell will heat up to small degrees, but usually that energy is locked in other chemicals in the cell and is utilized later. One of the major chemicals that energy that will be locked into is a molecule called adenosine triphosphate. You'll learn about that in biochemistry. Okay. So we can classify energy in terms of the two types of potential energy and kinetic energy, but another important classification of energy is from where it originates. So let me go through some important examples of this. And so, for example, if energy is found in chemicals due to their particular composition that they have, this is called chemical energy. So this is energy due to the structure of the atoms in the molecules and the arrangement of the atoms in the molecules in space. And so you will have particular kinds of atoms and particular kinds of arrangements and particular kinds of bonds between the atoms and the molecule that will render that molecule to have relatively high amounts of chemical energy. But then there are other molecules that aren't so lucky, and they won't have the kinds of atoms and the configurations, and so they will have relatively low amounts of energy. But that chemical energy in those molecules is potential energy. It's not so much kinetic energy. Thermal energy is another important one. So when you have a beaker of hot water in your hand, you are feeling thermal energy. Thermal energy is the energy associated with objects that are hot. Now, what makes the objects hot? So one of the things you may have sort of seen already, things are hot because they have a lot of motion. And if they have a lot of motion, it's because they have a lot of kinetic energy. So thermal energy, again, is associated with hot objects. Things that are hot have a lot of thermal energy. Things that are cold have relatively little thermal energy. There is also mechanical energy. This is energy associated, usually seen in large mechanical devices, such as, for example, pistons or bricks or things like that. So if you have a piston moving in a cylinder, its movement is going to go through a cycle. So you'll have alternating potential and kinetic energy in that cycle. But overall, that energy would be considered mechanical energy. And then a final type of energy is electrical energy, because this originates from the movement of electrons in wires, and so this would be electricity. And so this electricity can do work, as you probably know. It is a form of energy, so it is considered both potential energy and kinetic energy. Okay, so now I want to do is talk about the law of conservation of energy. So to introduce that, let me compare it to the law of conservation of mass. So one of the things you learned earlier is that for all chemical reactions, you have as much mass going into the reaction as you have going out of the reaction. And there should be no more mass or no less mass. So this is actually also true for energy. When you have a chemical reaction, you will have as much energy going into the reaction as leaving the reaction. You can have no more or no less. And so this is called the law of conservation of energy. So all chemical reactions and processes must obey the law of conservation of energy. Now, importantly, when you have some kind of reaction or process, although you must have as much energy coming out of that process as you have going in, you can change the form of the energy. So let me give you sort of an example of that, which is kind of an interesting example. So let's say you're looking at your car and you're considering the engine in your car, and you know that the engine receives a form of chemical energy. This chemical energy is gasoline. And so here I have sort of a picture here, sort of a diagram of what's going to happen. So let me sort of draw in here an engine here, and just to indicate here all this yellow energy going into the engine is chemical energy. And so this is the energy that is found in gasoline molecules. Now what the engine will convert the chemical energy into new forms of energy that are more useful. And so one of the forms of energy that's converted to is to mechanical energy. And so that allows the wheels to turn. Now interestingly, not all of the chemical energy that's going in the engine will be converted into mechanical energy. It's only a small fraction of it, say 25%. But the other 75% is released from the engine as well, and there that energy goes into thermal energy. And so it could be the energy is going to heating up the gas product molecules that are released when the gasoline is reacted in the engine. So that would be here, that'd be about 40% of the energy. Some of the thermal energy is being received by the coolant that the energy receives to cool down the engine. And then some of a small fraction of the energy, the thermal energy, actually is going to friction of the tires wearing against the ground. So what you can see is the engine, it can only take a small fraction of that 100% of chemical energy that's being added to it and only convert it to 25% mechanical energy. But here's the thing, despite that, all the energy that went into the engine can be accounted for. It is all going out. It's just that only 25% of it went to mechanical energy. The rest of the 75% went to thermal energy down here. So this is a perfect, wonderful example of the law of conservation of energy.